You're not the first to experience this, and here he is.
So therefore, I'm going to say it later, but whatever conjectures I'm going to present in the end are in fact theorems. So the general setup is that we have some compact Riemannian manifold, and throughout the whole talk it's going to be a surface, which means that it's two-dimensional. I'm never going to go beyond second dimension. And we're interested in the spectrum of the Laplacian, in the eigenfunctions and eigenvalues, to make the Laplacian form that we have lambda f to the left-hand side rather than subtracting it, and the corresponding corresponding eigenspace is denoted E lambda. So in this general setup, in case there is a boundary, then we add some boundary conditions which are either Dirichlet or Neumann or mixed conditions, whatever. So there is a general spectral theorem which says that there is an orthonormal basis of square sum rule of functions that we order according to the non-decreasing order of the eigenvalue. And to allow multiplicities, I write smaller and equal than rather than strictly smaller. So there might be multiplicities, but unless something interesting happens to the geometry of the manifold or the surface, there are no multiplicities. So I'm going to fix the notation capital N is going to the dimension. So unless something interesting happens to the geometry, N is always equal to 1. And something interesting is going to happen to the geometry because this talk is mainly about the torus. I mean, it is about the torus. So we're interested in nodal lines. The nodal lines are just the zero sets of some smooth function which is defined on the surface. And we're interested in the case that this function is some eigenfunction belonging to some eigenspace E lambda whenever the energy goes to infinity. Lambda goes to infinity. So what happens to the geometry of those nodal lines? And this question is very difficult and not so very well posed. So instead of saying roughly geometry, so the most basic aspect of geometry of the nodal lines is, of course, the length. And the length is the most basic and, in some sense, the easiest. But some other people are doing some much more subtle aspects. So you got recently a talk by Mikhail Sodin that spoke about a different aspect, which is the nodal domains. The nodal domains are the complement of the connected components of the complement. I'm not going to speak about it at all. So one small example that would clarify something, the example of separation of variables. So our surface is the two-dimensional torus. And we are considering functions which are separated by sine or acting on the abscisse and sine acting on the ordinates. The frequencies n1 and n2 must be integer to be defined on the torus. And it is easy to compute the eigenvalue, or minus the eigenvalue, is just a cousin of the sum of squares of those frequencies. And this factor is, in fact, 4 pi squared is not interesting. So it's easier to compute the nodal line factor. I mean, a product of two functions vanishes if and only if at least one of their factors vanishes. And then the nodal line is the grid. You can compute explicitly the length of the nodal line. And in fact, you can find out that if we normalize by the square root of the eigenvalue, this number, the length, is going to fluctuate between two constants, which seem rather arbitrary, but it is a fact that they actually fluctuate. In fact, however, this separation of variable is very atypical on the torus or anywhere, because if we take two functions of this type having the same eigenvalue, which is equivalent to sum of squares being equal, then we're no longer having this nice property, and we cannot then so easily compute the nodal line. But however, this example has some merit, and the merit is that in fact this is the correct rate of the growing of the nodal length. So this is the famous Yau's conjecture. It says that roughly that the line of the length of the nodal line is commensurable with square root of lambda, in the sense that there are two constants, small c and capital C, that it lies strictly it lies inside small c times square root of lambda and capital C times square root of lambda. The state of art about this conjecture is that first Brilling and Grams prove the lower bound, and then in the planar case, in fact, and then Donley Pfefferman proved the general upper bound and the lower bound, just in case of the real analytic metric. This conjecture is still very much open for the C infinity case, so it would be a great achievement. Anyway, there is the following general conjecture, which I believe belongs to Zeldich, that the nodal lines are in fact equidistributed for generic chaotic manifold. In the sense that, for example, if you take some submanifold, then the mass, not the mass, then the length of the nodal line that is falling inside the submanifold is proportional to its volume. And this conjecture is very much in the spirit of Schneermann's theorem, which says that the mass is equidistributed, but it doesn't follow from it. And in particular, as a particular case of this conjecture, the nodal length is supposed to have asymptotic of this type for generic chaotic manifold. So it's not so if we divide it by square root of lambda, it doesn't just fluctuate between constants, but two constants that depend on the manifold, but it also converges to the constant. So this conjecture is obviously false for completely integrable systems such as torus and sphere. I just gave an example where different sequences converge to different, to genuinely different numbers. But the question that one may ask is whether or not this conjecture is correct on the torus for a typical eigenfunctions. I mean, perhaps there is some kind of concentration result. And we are going to answer this question. In fact, we already answered this question in the earlier paper. So it is also important to introduce the following random wave model due to Berry, which is supposed to model any eigenfunctions on any generic manifold, chaotic manifold. So suppose that we are given some lambda, then we compute the square root of lambda, and we construct a superposition of many plane waves that have the same wavelength or wave number that they have with square root of lambda, with random directions and random phases. So those phases are random in the sense that they are equidistributed in 0 to pi, and the directions are the same. And the claim of Berry is that the typical eigenfunctions behave exactly like typical representative on this, or rather, all the eigenfunctions on a typical chaotic manifold behave like a typical function in this random function in this ensemble. So for any instance, if you choose any theta or any psi, this function would satisfy the Laplace equation on the R2. However, you cannot possibly define this thing on an arbitrary manifold. So, for example, if you take the torus, then since those frequencies are not lying in lattice points, then it's not going to be defined on the torus. So this statement is quite vague. And the other way to define this ensemble, so for those that the word random field, Gaussian random field, says something, then this is just a Gaussian center random field with a prescribed covariance being the Bessel function with this factor square root of lambda. So these two ways of defining this ensemble are equivalent up to, you have to explain exactly what is the meaning of this limit j goes to infinity. And once you send j to infinity, this ensemble is indeed Gaussian by the central limit theorem, because you add random variables which are identically distributed and independent, and then it is supposed to be Gaussian. So those two ways are equivalent of defining, and each one can, the physicists work with this way, I work with this way. So what was the statement of Berry? So the statement of Berry is the following. So suppose that M is chaotic, and chaotic, for example, doesn't obviously include torus or the sphere, then suppose that we would like to model a deterministic eigenfunction f with highly excited eigenvalue lambda, high energy eigenvalue lambda. So instead of considering this function, what we are going to consider is this random element with wavenumber square root of lambda. So, and we can measure different statistics. Instead of measuring it here, we measure it here. And the right-hand side is already been introduced before that in the history. So first it was studied by Rice for one-dimensional case. So Rice was an engineer, and this is the Rice of the Katz-Rice formula. So he studied this thing in order to understand the occurrence of exceeding some levels. And Longyat Giddings also used the two-dimensional model in order to model ocean waves. And this ensemble was already studied, and this random wave model inspired to study it as a model for eigenfunctions. So suppose that I want to predict some quantity, then I do it on the right-hand side. And so this was used by Berry, Smilansky, Bogomolny, and their co-authors and some other people to predict the behavior. Now, there is no rigorous statement in this arrow, so there is no rigorous proof of that statement because there is no statement.
But is there a rigorous proof within this random wave model about the structure of the little line?
No, so for example, I'm going to speak about the length. Yes, for the length there is. You can study the curvature, you can study other parameters. But there's no rigorous proof that whatever you measure here.
No, I understand there's no connection. You can't make a connection, but you can analyze
yes.
fairly accurately what
Yes.
happens.
This is rigorous deterministic.
That's what I meant.
Yeah, so
anything that the Rice formula like local, that's what he's like. Anything
But
local,
number of domains, but number of
domains, that's of course very
so this is exactly what I wanted to say. So for the number of domains, you cannot possibly study it for the random wave model, and this is precisely why Bogomolny introduced the percolation model, because you can do it for the percolation model. And percolation model is the model of this. Sorry, is the model of this, which is the model of this. So percolation of model is a model of a model. But but nevertheless, it gives the answer. And the reason that he has to introduce the model of the model is because they couldn't possibly compute this precise quantity in the model.
Nobody knows how to. It doesn't mean you can't do it.
Right. Okay. Right.
That limit people. I mean, Sutton did something. Right?
Yes. But Sodin did it for the random spherical harmonics. But he can do it probably. Yeah, you're right. So since I'm interested in nodal length, then I would like to survey the results for the nodal length in the random wave model. So how we are supposed to act? So suppose that we are given a manifold. For example, we are given the torus. Then we have to choose a planar domain that would represent this this manifold surface. So it is sensible in case of the torus to choose a rectangle inside the plane. That's sensible. Okay, so then what we have to do is introduce this random variable L, which is going to take into account the random instance of this function, compute the nodal line, and then compute the nodal line of the nodal line. This is a number, this is a random variable, so we can study its distribution, and hopefully its distribution is going to represent somehow the values of the length for chaotic systems. And then, so Berry computed the length. The expected length was commensurable with square root of lambda. If that would be a different power of lambda, then it wouldn't be consistent with Gauss conjecture. And then Berry actually argued that the variance is supposed to be logarithmic with lambda, which is much smaller than both the square of the expected length, and it is also much smaller than whatever one would expect the variance would be. One would expect the variance to be actually proportional again to square root of lambda because of the natural scaling. But some miracle has happened, which is called nowadays as Berry's cancellation phenomenon, that caused some cancellation in the square root of lambda order of magnitude, and then we get the second term, which is logarithmic. And the same miracle actually happened if you study the random spherical harmonics. But the question is whether or not it's going to occur for the torus.
But now, go back to that for a second. Well, if U is small, shouldn't I have a U dependence on the right-hand side or not?
Yes. So the constant. You mean invariant?
No, an expectation.
Yes, the constant is proportional to the volume of U. I just didn't want to present it. And
U is fixed.
U is fixed, but I mean, can you actually get?
Yes.
You can actually prove that it's proportional to U.
yes,
Like
and the variance is also proportional to the volume of U,
That's all.
but not, for example, to the square of the volume. It is proportional to the. This is for the introduction. So far for the introduction. Now I'm going to really speak about the problem that I'm dealing with. So what is the random eigenfunction on the torus? So on the torus, there are so torus, first of all, we denote it as t squared. Is it the dimension standard torus is R2 over Z2. And then we have all the complex exponentials, the complex eigenfunctions, where mu, the frequency, is a lattice point in Z2. Now, if two lattice points, it is easy to compute the eigenvalue, which is the cousin of the squared length of mu. And if two of those have the same length, then we can add them. In fact, we can add as many of those as we want, and endow the coefficient, the space of coefficients, with the Gaussian probability measure. And this beast is called arithmetic random wave. So here, to make it real valued, so we assume that all those a mu are going to be Gaussian IIDs, standard Gaussian complex IIDs, safe to this relation that a of minus mu equals to a mu complex conjugate. This way we get something actually real valued. And we have here the relation is that, so if we assume that all of mu's squared, the square length is an integer number m, then the relation between the eigenvalue and m is this relation. I'm going to write it on the blackboard. So whatever results I'm going to present are going to be in terms of either lambda or m, and I can use them both. And my rule for presenting the results is that whenever the dependency is going to be analytic, I'm going to write it as a function of lambda. And whenever it's going to be arithmetic, I'm going to write m. That's my rule of thumb. So, of course, with this writing, we can obviously write it in a real valued form, which is much longer. And this precisely explains why I prefer the complex form, which is much more compact and elegant, but it's the same. And then we need the following notation. Mu is going to run all over lattice points inside the circle, and n is the number of those lattice points in the circle. It is also the dimension of the corresponding eigenspace, and it is also the number of representations of m and sum of two squares. All of those are the same. So this is just a reminder, what is a random eigenfunction. So if we want to speak in terms of random fields, then this field is stationary, Gaussian, but it's not isotropic if it says something to anyone. I'm not going to say anything else about it. But, anyway, so the covariance function is this arithmetic function. The definition of the covariance function is that this is just the covariance between f evaluated at y and f evaluated at y plus x. So it depends only on the difference between x, y, and the other point. And this is this arithmetic function. I just sum all the cosines with the frequencies. So this is the covariance function. And I could have, a priori, I could have just specified this thing without giving the concrete realization. And it is completely the same. And I'm going to denote the space of frequencies, the set of frequencies, lambda m. Those are all the points on the circle which happen to be also integer. So just a little bit about the dimension. I'm sure that most of the people know it, but I will still survey it. So as I said, this is the number of representation as 2 squared. And given the prime decomposition of this number m, we can effectively compute it. And on average, n is square root of logarithm of lambda. Now here the average is taken over on all those m that are representable as sum of 2 squares. Because otherwise this is just an empty space, and there's no point to average over empty spaces. There is no point there. And this result is due to Landau in the beginning of the 20th century. This number n is fluctuating erratically. For example, there are sequences m, so that the number m converging to infinity, so that the number n is 4. It cannot be possibly less than 4 because of the symmetries. But 4 you can attain even if m converges to infinity. For example, for prime numbers. And this number, so it fluctuates erratically, and also the set lambda n is fluctuating erratically. I will explain in the next slide what it means, actually. And throughout the whole talk, I'm going to assume that n goes to infinity. If n doesn't go to infinity, then you cannot say much about it. I mean, you can still say something, but we are going to assume that n goes to infinity. So now I'm going to speak about what it actually means that this set of frequencies fluctuates erratically. So there are two possible extremes. The one extreme is that if we project all the circle with radius squared of m on the unit circle, then it's going to be equidistributed. That's one extreme. And it happens typically for a density 1 sequence of m's. But there is another extreme. Even if we assume that n goes to infinity, the lattice points on the circle might concentrate just on 4 angles. And this I call Cilleruelo sequence because Cilleruelo was the one that proved their existence. So I think it's fair. And more formally, for every m we define the discrete measure, which is the delta atomic measure supported on the unit square with the points, with the projections on the points on the unit square or unit circle, and we divide it by 1 over n to make it a probability measure. And then, so the equidistributed sequence means that this probability measure sequence is going to weakly converge to the Lebesgue sequence or Lebesgue measure on the circle. And the Cilleruelo is going to converge to the atomic measure, supported in those 4 anti-podal points. So these are the two extremes. But there are also things in the middle. We're interested in getting also the results for things in the middle. And it is quite reasonable, even though like we didn't study that in depth, but it's very reasonable that the set of all the attainable measures nu, where attainable means that there are limits of sequences of discrete measures of corresponding energy levels. So it's reasonable that the attainable sequences, attainable measures, is a continuous connected set. So if you define some kind of function on this set, it is reasonable that the image of this functional is going to be an interval. And it is also reasonable that whatever results we get here and here, these are the most extreme results. So the question is whether we can formulate these results rigorously. So some earlier results. So this result that I promised, which is joined with Zev Rudnik. Again, we count the nodal length of the eigenfunctions, and this is a random variable. We are interested in this in its distribution. So and recall that Yao prescribes that this is supposed to be commensurable with square root of lambda. So whatever the expectation is going to be, it is better be some constant times square root of lambda, and this is indeed the result. This is a very easy application of Castrais formula using the stationarity and everything. It's a standard computation, and in fact, it's not asymptotic result, but precise result. And now the question of the variance.
This is true as long as n goes to infinity.
No, any sequence. So you don't have to. This is a precise formula. Inside.
In terms of the expectation being, you need more variables.
No, I don't think so. Maybe you need more than 8. Maybe you need 16. No, but I mean to avoid some degeneracy.
The average is some constant. Yeah,
I mean, but this result is precise.
yeah.
In my opinion, it holds even for 4 points. I can check it if you're very interested.
It's about Gaussians.
Yeah, it's an average for Gaussian, even for finite.
And this is just a standard computation. You cannot impress with that anyone. Now, the first theorem that I'm quoting, this is the earlier result, that you can bound the variance by O of lambda over square root of n. I assume that n goes to infinity. Otherwise, there is no meaning to this bound. And I claim that this answers my first question, whether or not there is a concentration. So it's very easy to check that since this thing is much smaller than the square of the expectation, then there is a concentration result. It means that basically the constants in the Yau's conjecture might have taken you can take them as the same, basically, with high probability. And we made the following conjecture, that in fact the variance is asymptotic, or the variance is O of, you can improve this bound, lambda over n, and we wrote it in our paper as an O bound, but in fact we thought that there is going to be asymptotic over this side, and I'm going to show you in the next couple of slides how much we were wrong actually. Anyway, at some point we proved the following result. So this is joined with Krishnapur and Kurlberg, that the variance is equals to some constant times lambda over n plus lower order terms. So similarly, to resolve this conjecture, so all we had to do is rule out that the possibility that C vanishes, and it does not. I mean, it does vanish. And this is called the arithmetic Berry cancellation. This is the same, it has the same nature, but it's slightly different appearance as the usual Berry's cancellation phenomenon. And this is was supposed to be the leading term, but it just vanished.
So how big is the lower?
So I will show it in the next slide. Now, so this is the answer to your question. So the next term was of order lambda of n squared, and in fact it's the best possible upper bound for the variance. Why it is the best possible upper bound? Because of the next result. Theory. There exists a density 1 equidistributed sequence of energy levels, so that we have this asymptotics lambda j over n squared, where the constant is 1 over 512. So therefore, you cannot possibly hope to improve this upper bound. And so this is a result for equidistributed sequence. The result for Cilleruelo, there exists a Cilleruelo sequence so that this constant is 1 over 256. times the same power of lambda over n squared. So now one small remark that in both these results I-state exists. I didn't say that for any equidistributed sequence this holds. So out of the density 1 equidistributed sequence, we extract another equidistributed sequence which is of density 1 again, and then this result holds. And the same thing for not every Cilleruelo sequence. At least I didn't claim it until yesterday. That this variance is asymptotic with this constant. So, and since yesterday, or since Jean Bourgain's result, this thing is actually.
I that was probably today. It usually works at 3 in the morning.
Yes. I think that I got the email at like 3 a.m. or something. But like.
Very slow sometimes.
But I read it. Anyway, so the condition was supposed to be what I was supposed to present. There is some arithmetic condition that I'm going to present, and then I'm going to present its solvability by Jean Bourgain. But nevertheless, so these results are for two extreme measures. The question is, what happens in the middle? And we have an answer for that as well. So this is just a repetition of the previous slide. Okay, so C is supposed to be between 1 over 512 and 1 over 256. That's a mistake here. So for every, we can construct a sequence so that there is an asymptotic of this type. And in fact, after yesterday, these are the only ones. So in fact, what this, again, due to Jean Bourgain. And again, it shows that all the sequences converge if they converge to some limit times lambda over n squared, then the constants are taken from this interval, and the extreme measures are the Cilleruelo and the equidistributed measure. So I would like to introduce a so-called unified formula that would include all those results, and modulo Jean Bourgain results, it will imply this theorem and some stronger results. So recall the covariance function, so some arithmetic aspect. Recall that the covariance function is the summation of cosines, and this lambda m is the set of frequencies. So I defined am using A4m. This is an arithmetic quantity that measures something that looks horrible in this writing, but it looks much less horrible if you write it this way. So if you have a circle of radius square root of m, and you have 2 points, mu1 and mu2, two vectors, mu1 and mu2. So these are, you can think of it as points here or as vectors. So this is going to be theta of mu1 and mu2. So all this what this quantity measures is the fourth moment of the cosine of the angle between mu1 and mu2 whenever they are chosen independently uniformly in those lattice points. That's A4 of n. So perhaps I would write that. Sorry. So this is just the fourth moment of this one. This is an arithmetic function. And another function that I have to, another quantity I would like to introduce, R6 of m. R6 of m is just the sixth moment of the covariance function. In fact, it equals to this set 1 over m6 squared, 6m to the power 6 of this set S6m, the size of it. And S6 of m measures the relation of size 6 of the spectrum correlations of size 6. So it is very easy to prove that S6 of m is O of n to the power 4, and if we divide it by n6, that is equivalent to R6 being O of 1 over n squared. The crucial question is whether or not you can actually improve this bound. So I would like to write R6 m equals to 1 over n.
By sigma, yeah, you just mean the code argument? When you're doing the L form?
Sigma is just I sum them as vectors in R2.
Yeah.
This is not length. I mean, equality of two coordinates. And S6 is mu 1 up to mu 6. So that sigma of mu I equals to 0. So these are the spectral correlations. And then I have the following result, which I call unconditional arithmetic formula for Nodal length variance. The reason I called it unconditional is because some results that I was going to present are going to be conditional up until yesterday. And I mean, at this point, probably there's no point to call it unconditional arithmetic formula for anything. But this is the state of art. So this is the formula. So the first term is factored by, multiplied by lambda over n squared, and the second term is O of lambda times something. So it's better than the something R6 be small O of n squared. If yes, then this is going to be indeed an error term. So this is indeed why I want a non-trivial improvement of this result. And the other thing is that this quantity is better to be, bounded out of 0, because otherwise, and indeed this is the case. So in fact, I'm an honest person, so every time that I lie, I confess about it. So in fact, what is there is R5, and not R6, but it is easy to do some Cauchy-Schwarz trickery to reduce it to R6. And the disadvantage of R5 is because it's not spectrum correlations anymore, because you put absolute value on the moment of R, and then you cannot speak about it in terms of arithmetics. So it indeed, if you take some sequence of energy levels, it implies, so this result implies asymptotics, provided that two things happen. So A4 has to converge to a limit, which is bounded away from quarter. And R6 has to be smaller of 1 over n squared. And the first condition is in fact easy. I'm going to solve it to explain it in the next slide. The second condition was difficult up until yesterday, and it's still difficult for me. So therefore, I made a correction to my slides. I added the double quotation. Difficult. Anyway, so given a probability measure on S on the circle, nu, you can define the same analogous quantity A4 of nu rather than A4 of m. And then we have this equality, obviously, A4 of mj is the same as A4 for the corresponding discrete probability measure on the circle. And if the probability measure converges to something, then the corresponding A4 converges to that something. And this is the whole story of A4 models. And now the only thing that we have to study is what about the A4 of measures. And this is relatively simple. So first of all, you can rewrite it as the 3 over 8 plus 1 over 8, the square of the Fourier transform of this measure at the point, the special point 4. The reason it's 4 is because it's A4, it's the same 4. And it is very easy to give, using this equality, to bound. So this is why I wrote in the earlier slide 3 over 8 and 1/2. A4 is between 3 over 8 and 1/2. And in a more human writing is just that this number is between 0 and 1. And in fact, it's real. I mean, it's not a complex number. And this is very easy to do using, so the upper bound is using the triangular equality, lower bound is just, well, it's a square of a real number. And both of the limits are attained by uniform measure, the lower bound and the upper bound by the Cilleruelo measure. And these numbers are bounded away from 1/4, so we need not worry about that. And in fact, we can also construct admissible measures with this thing. And the only question about them is whether or not they have this bound for R6. So up until yesterday, we were able to okay, so now the second ingredient, which is R6. Up until yesterday, we were able to do it for generic sequences, and Jean Bougain was able to do it for anything. So we were able to construct a density 1 sequence with R6 bounded by small of 1 over n squared. We were able to do it for some Cilleruelo sequence. This is why I say exists. I didn't say any equidistributed sequence. And we made so now it's conjecture with double quotation because it's a theorem due to Charles-Bougain. So that this fact is always small o of 1 over n squared. In fact, I write it the quotation correct rate as 1 over n to power 3 minus epsilon, and maybe we can some people in the audience think that we can actually drop the epsilon, and I agree. I mean, I don't argue with that. So this is apparently, and this you cannot possibly improve that because the diagonal solution come from that. And now I'm going to formulate some unconditional results since tonight, and I'm going to assume this thing. What is going to be consequences of that? First of all, there is the same lower bound. I mean, there is the lower bound lambda over n squared, so everything is commensurable to this quantity lambda over n squared. If there is convergence of measures, then there is this asymptotics, where C is an explicit prescribed constant. And the set of all the C's that appear in front of the asymptotics is exactly this interval between 1 over 512 and 126. And this is the last slide of non-mathematical talk. And probably for the mathematical talk, I mean, presenting the proofs of the stuff, I won't have time, probably. So if you remember, I introduced the equidistribution conjecture of Zeldich, and particularly it implied asymptotics for the nodal length. So I claim that, and I actually already said that, in fact, it implies that 100% of functions on the torus satisfy this asymptotics. And this is just, well, we normalized it to have expectation 1, so the variance vanishes. And then the variance that vanishes, it means that exactly the lengths are concentrated around the constant times square root of lambda.
I thought the other conjecture was about the distribution of the nodal set rather than its length. Yes, whatever you said was zelf.
Yes.
I thought that was a statement.
Yes,
not
yes, yes.
about what, it doesn't matter what the length is, it's just where are they located. So
Yes.
What are you saying here?
So two remarks about that. So I said that in particular, the length is also has asymptotics. That's a particular conclusion of the second distribution. The other thing is that instead of studying the length inside the whole torus, you can study the length inside some subset, and you can prove the same results.
You can localize them.
Yes.
Okay.
So in a way, it is equidistribution.
That's Zelda, whatever the Zelda statement that is, it's a weaker statement.
Yes.
I mean, equidistribution may be true. It's just a question of locally behaving.
Yes. Yes, I agree. Anyways, so here I use the following principle. I call it. I will write what I call it. So suppose the sum property X holds for generic eigenfunctions on all completely integral manifolds. And by the way, this principle might be completely bogus. I mean, I'm not claiming anything. I just made it up. Then the same property holds for all equidistribution, all eigenfunctions on generic chaotic manifold. I mean, it might be correct and it might be wrong, and it might depend on the property X. I call it.
Sure, it's false.
Sorry?
It's false.
Probably it's false.
I
Yes.
mean, you can take arithmetic chaotic. Well, I guess generic chaotic. Okay, sorry. That's a savior.
I mean,
Yeah,
but
it's true, yeah, but not because of the causal connection.
probably this principle is false, but
No. I mean, I think both if A implies B and B is always true, then it doesn't matter what A is.
okay, fine. Anyway, I call it word commutativity because I just more or less arranged the word generic and all in different order. And I think that this
Seem
is
to be suffering from wanting to draw a commutative diagram.
yeah. So I think that this is the last slide of this talk. So thank you very much for this.